Siamo di volta. Aqui você pode ver a expectativa de zogue lá, como vai ser o futuro. Eles usaram esta sol significa boa perspectiva positiva para o país, isso significa perspectiva negativa para a Inglaterra, o Brexit, não quer mais trabalhar com energia solar muito, não expecta muito crescimento, meio, e para o Brasil está boa, acho, cadê o Brasil? Está insulado, agora a expectativa é English, okay, English. Sorry, I was speaking the whole time in Portuguese, and the people asked me something at the coffee break. Okay, the outlook for Brazil is here. Now they have installed 1.1 gigawatt total installed, and then they expect until 2022 additional how much? Almost 8 gigawatts. So new capacity 7 gigawatts. So this is a big. So the outlook is really positive for Brazil. So we'll from 1 gigawatt to 8 gigawatts, a really big jump. Within a quite short time, then, just 3-4 years now from now. This is from 2018. This is quite new. Okay, this is. These are the actual data, and this is previous summer. This is forecast yesterday. This is just a bit older, with 2015, and this is how to really implement photovoltaics. This shows the policies, and during that period, most of them was via feed-in tariffs, so premium tariffs. Just as I explained before, you pay a fixed rate for a period of time, for example, for 20 years, and this attracts really investors. The other one, which is a bit more modern, is the net metering, as you have in Brazil. So you get a one-by-one tariff. So if the tariff is increasing, you will also get more for your energy, solar energy being produced. So this automatically compensates that. Also, there is automatic inflation compensation. So if there is inflation, then the tariffs go up, and also the recompensation for your solar energy generation goes up also. Brazil, you don't get any money for that, you only can compensate your actual consumption by that. And also there's now the discussion whether the consumer should pay something for the grid or some taxes and so on. Possibly that's only weakening that program. Theoretically it's quite good. If it's a real one-by-one tariff, just by calculation also for the companies, it's quite good, so they can make a quick estimation about the profitability of such a plant. If you have more things involved with grid fees, with taxes and so on, it gets more complicated and possibly less used. Subsidies, flexible, so this is also some other measures. The PPA is directly related to that, but the PPA is more a direct contract between one producer and the utility. This is the electricity costs for 2016. So you see here, residential PV is quite expensive, commercial is quite competitive to coal, nuclear, and so on. And this is interest rate here. You see here a 3% interest rate. We have that price here for the vicinity of 10 euro cent. No, this is US $100 per megawatt hour, or 10 cent per kilowatt hour. If we have 10% interest rate, it's more realistic for Brazil, so prices go double. So the impact of interest rate is really big. It's much more important if you talk about here technology. If you improve the efficiency by 1%, it doesn't have a lot. If you have high interest rates and prices go up by 100% only due to the interest rate. If we can lower the interest rate by 1%, it's much more use than we increase the efficiency by 1%. So nowadays here we are here, so this is achieved in 2015, $30 in the Emirates. So this is not really actual anymore, it's 2016. So what's the suggestion more or less by me? Just we can also, in order to achieve the best possible cost. So I guess can do something quite interesting. We would call it the eBay for energy, or the Airbnb for energy. If you have a house nowadays with photovoltaics, usually you are fixed to the feed-in tariff, which is very low now in Germany, about 20 years. Or you can do own consumption, so you use it directly. But why not, if you, for example, go on holidays for 6 weeks, why not selling that electricity to your neighbor? You just pay a fee for using the grid, and like you do for RBB or eBay or something like that, and then sell that electricity to your neighbor with a direct PPA. Or here you can, this would be very fertile for startups. Here you can just make a provider of stored energy. So you can have your own storage power plant, like a pumped hydro storage power plant, a small one, and then you purchase electricity on the market depending on the price. You can do it automatically via, for example, a least cost router or something like this, and then sell it for a higher price, and so on. This is only done now by very old companies which only allow a very limited amount of players. But why not make it possible for all of us to go on this? And this will also trigger a lot of innovations which don't occur at the moment. I've been asked why is not happening something in Europe now more. This is due to that because the system is still the old energy system where only a handful of players is there, and they don't want that anyone is interfere. They don't want such a thing where a lot of startups and so on work with it. So you don't have any governmental contracts, which just do speculating a little bit on the eBay market, and then you can also make new business models and schemes and so on. Also what you can do, for example, is a load management. So you can say, okay, I switch my load from nighttime to daytime, so you can profit more from solar tariffs and so on. So this is also possible. So this gives a lot of opportunities. At the moment, the system is very inflexible and doesn't allow that. Cost structure, I've been mentioning also, so if you take nowadays, if you buy electricity in Germany, I think Brazil is similar, it's only about 23% are for generation of electricity. It's a minor cost factor. Much more cost is related to transmission distribution. So here you can save much more. So we always talking about how, I always get asked how we can improve efficiency, how make solar much cheaper from 2 cents to 1 cent. But this doesn't matter so much. Here, this is the main cost factor, how we can reduce the cost. Also, here, we think consumption and generation at the same time important. So we have some synchronicity between production and consumption. This doesn't happen at the moment. This works totally independently, and therefore the cost of the grid system is quite expensive because it has to level out that differences. So this is, for example, here in Germany, you see just a couple of days, I think that's 1 week here. So you see here you have, here is the share of conventional power plants, here are solar power plants, and the light green here are the wind power plants. You see during daytime it's quite good. Then you have already, there's a lack of energy because there was not a lot of sun, so they imported something from Poland and so on. Here is a lot of solar energy, so they exported some energy. So this is also why do they export? Because the conventional power plants couldn't throttle down sufficiently. This is a bit lack because they have been once built in the 60s and so on. Nobody thought about such a scenario. They think they will work for 50 years and so on, and nowadays you have to tell the operators 8 hours in advance that they should throttle down or go up and so on. It is a very inflexible system. But the future is flexibility. At the moment it's not paid because just at the moment is it just paid for energy, not for the flexibility options. And this is a discussion, it's a very, very slow discussion. But here you see the effects of that. So the conventional could slow down. So here Brazil is much more advantageous because you have hydropower plants which you can ramp up and throttle down within 1 minute only. So they would be much more adequate for fluctuating wind or fluctuating solar and so on, and you wouldn't have that problem that we have in Germany. So if we take this Friday here, so you see a lot of solar power here, and due to the overproduction here, they have to export for a very cheap price. We take a look now at this Friday, 2nd of August, We see here the solar production here. This is solar irradiance here in Germany, and you see here the costs here, the electricity price. See, it's when the solar irradiance is low, the price is high. As soon as we have this 40 gigawatt online, then prices go down. So that's an issue. So the solar, if you sell solar electricity on the market, you only achieve a quite low price. The idea is just we have to also modify the power plants a little bit. So from strictly south, it would be equivalent to strictly north orientation of the solar power plants, which gives the maximum energy output during the year. We should think about something else. For example, to do east or west orientation. So this is traditional solar power plants here, looking in one direction only. So here's, for example, east-west orientation. So you have more power output in the morning and more power output in the evening. A little bit less at midday. So from the energy point of view, it's less power output, but from the financial power output, it's more. So here you see the prices here. So here you produce here more. So you can get you get the bigger prices. You lose something here. So here you see this effect here. You get the azimuth here first only on south orientation. If you orientate more towards east, so you have the maximum at 9:30. It's a bit lower here compared to that. So you can profit from high energy prices there. Also the grid system is much more balanced. Also from the afternoon, if you have here your system with an azimuth of 225 degrees southwest directed, so you have here the maximum at 2:40 p.m. And this is much more helpful, so you can financially this helpful to direct. Or what you can do is here's some tracking system. So usually tracking system is a bit outdated because the cost for the tracking system is now more expensive than the additional 30% of cheap solar modules. But if you consider this, it might be some kind of renaissance of the tracking system, because you can create more power output in the morning here or in the evening here. If you see this line, so this is 30 degrees dual axis tracking system. So this is quite helpful here. Here you have the traditional 30 degrees south orientation here. This is told you east and west orientation, and so east-west orientation, which would be equivalent to this is east-west orientation power plant. So this is also things we have to consider. Not only think about energy production, efficiency, and yield, just also when is the energy being produced, and whether it's helpful for the grid system, or even think about the market prices that occur in the morning and evening. Also, you can think about seasonal changes. So this is the different months from January until December in Germany, and this is electricity consumption. In Germany, we have the highest consumption in winter, because we have sometimes electric heating and so on, and we don't have so much cooling. So the gray line is the consumption, and we consider just if we tenfold our capacity now, we have 40 gigawatts, this is 400 gigawatts, so that we really, almost everything goes to a whole energy system, theoretically, is photovoltaics. So we see here, if we have a 30 degree of elevation, we have a really big overproduction in summer. So we have produced much more energy in summer than we need. So if we incline it more from 30 degrees to 60 degrees, then we're to use the summer surplus, and we have some additional power in winter. Here it doesn't look so much, because it goes up from 10 to 40, but it's actually quite a lot more. It's about 24% more or something like this. So there's really some significant increase in winter. It's generally low, so but relative increase is quite a lot. Here you see it, for example, here elevation angle. So if you go to 30 degrees in January, we have 67% more than for horizontal. If you go to 60, we have the double than we have for horizontal in Germany. In July, so it can get worse. So if you have high inclination, so therefore you can explain the reduction by 14%. There's also an idea how we adapt our PV power plants not only to maximum power production or maximum energy production, but to equalize the daily and seasonal changes. Also another thing what is heavily used in Germany, about 50,000 systems have been installed like this, just to partly disconnect from the grid. So just to, while many people are at work and you have your PV system, so you cannot profit really from the electricity being produced. You can only sell it to the grid, which pays a very low rate, only 10 cents per kilowatt hour. In the evening you come home and take energy from the grid and you pay 30 cents per kilowatt hour. So you have a huge difference between that. Why not store it? So even if the storage is expensive, so you buy a battery, a chemical battery here, put the energy from daytime here, and evening you can watch TV with your own created PV energy. So it's like a solar home system from the 80s. Yes?
There must be a limit for the introduction of solar, I suppose. Assuming that you don't have another way to control the frequency stability problems that it would cause. I would like to know what's the limit that you have calculated for Germany, for example.
Yeah, Germany always. I remember about 10 years ago, they say limit is 2%. It's a complete lie. They always say there is a limit, but there is no limit. They always invent limits in order to limit the competitors. So they always said, yeah, you still have this newspaper from the Association of the Concessionaires Germany, made in 1990. They say you never can make more than 2%. Now we have already 36% of renewables in Germany, wind and solar principally, and there's still no problem with the grid stability. Even the grid is safer now than it has been 10 years ago. There is this stability indicator, and it increased even. Basically because we have double production, but this is not the case that there's a limit. And there are some countries which are really, for example, Denmark or Scotland, they have more than 70% of wind power. Some weeks, or Portugal even. Portugal is also running a couple of weeks which is just renewable energy. It's basically solar and wind. So it's possible. For Germany, it depends on the flexibilities and the storage options and so on, and the interchange between neighboring countries and so on. Germany doesn't have a lot of mountains, they have some mountains. So, but for example, a connection between Germany and Norway, there's a lot of lakes there where you can store energy. You pump up the water during high availability of solar power and take it off during low periods of solar power.
Okay, but I mean, it will be necessary to work on storage.
Yes. So depending on whether, the discussion is whether you build the storage expensively in Germany or whether you get it cheap to put somewhere else. So this is discussion. So there's now 2 power lines being built, each one of 1.4 gigawatt to Norway. So this helps a lot. Or there's already very well connected to Switzerland and to Austria, where we also profit from there's some problem is in Switzerland there would be more opportunities, but there is no investment in additional storage power plants because the prices are so low. It's a bit the problem. The prices are so low because there's not a lot of flexibility of the thing. So the conventional power plant owners let their machines run even if they go on the negative side. So they don't run profits, they just run because they are not flexible enough to really be coping with profitability, and therefore prices are extremely low. Sorry, I have to continue a little bit, so I can, sorry. One question, quick question.
Okay, sir. I have seen a report according to the United Nations. They said that those mirror buildings are endangered the migratory birds. So I would like to know the average brightness of solar photovoltaic panels. Okay, let me put it again. In this way. According to the United Nations, there is those buildings with the mirrors made up of mirrors are endangered the migratory birds. So I would like to know the average brightness of photovoltaic panels. if you cannot also put in danger the migratory birds. Because I can see in this mesh that you have on the slide.
We made some studies about that, about the reflection. It was not only for birds but for airports. You can put anti-reflection coating, so the efficiency even gets better from the solar modules, and then you don't have that problem anymore. This depends on the surface treatment of those. You can do microstructuring of the surface. And for birds, we didn't observe any bad impact. It was just for, as you saw this building before in airports. Some of them airports are still operating, so a lot of solar panels around them. But the pilots said they want to avoid reflection, so the solar panels have been treated with anti-reflective coating on the top. But for birds, we didn't. These are more related to wind power. Okay, but I have to continue. Sorry, we just otherwise we have time for questions a little bit later. Otherwise, I can't come to research at the end. So this is just the thing that you can reduce your grid use by 60% by using storage. If you use it directly without storage, only PV, you can reduce it here and average by 30%. That's just quite numbers. Just a normal average German household for a person, 4,500 kilowatt hours per year of consumption, a PV generator of 5 kilowatt and a 4 kilowatt hours of storage. There's also something important really to think about if you go for grid friendliness of such storage, about the charging regime. So some of the systems, they are made quite simple, and they just start to charge, when the sun is available. So the morning they start to charge, and then they are full at 11 o'clock, and then you still have the peak here, which the grid has to digest this peak, which has to even increase the fluctuation in the grid. You do not reduce, if you have this charging regime, the high fluctuation in the grid, you increase that, and this causes more balancing costs in the grid, and finally more cost for the customer, which is already very high. The other way, just if you have the same configuration, just to change the software a bit, you just tell them here, okay, you don't charge in the morning because you have scarce of photovoltaic energy. You just start charging at 10 o'clock or so, and then you charge, you don't stop charging at 11 o'clock, you charge until 3 o'clock, and then the battery is full. And then you cut this cap here, and you cut this peak here. And this is the same configuration, but you just change the software and said, okay, we want to reduce fluctuation caused by solar energy, and also it's beneficial for the house owner because he can use that energy in the morning before the sun sets and in the evening to watch TV or so. So it's also an issue which is relatively new, so you should also think, and then you have the grid capacity increased, and if a reduction of peak injection in general makes it cheaper. New markets, diesel. So there are 500 gigawatts of diesel power plants installed. You can substitute them by photovoltaics. Let's take a look at that. Where are lots of diesel installed? So some countries, they rely here, like Somalia, they rely 100% on diesel power. Also some mid-African countries, or here Madagascar, or here's islands here, also the Caribbean, they rely a lot of diesel power. And let's see how we can substitute them via photovoltaics. So these are the costs. So this depends on the diesel price and so on. And so we made here a map here where they become competitive. So green and yellow means competitive. This is a bit older. This is from 2012. Now it's even better. So some part of the orange is already also competitive. You see here, so very large, especially Brazil. So if you don't have any subsidy for diesel, photovoltaic is competitive for the whole country. So photovoltaic is always cheaper than diesel power. This is here not the case. This is Venezuela. This is where diesel is cheaper than water. So therefore you're not competitive because it's too cheap there. Diesel. It's heavily subventioned. Also some African countries here, or here, sure, the Middle East here, Iran, Saudi Arabia, and so on. Sure, gasoline is too cheap there, and therefore you cannot compete with photovoltaics here. But for most part of the world, including Brazil, photovoltaic is easily competitive. Here here you see the costs here. This is a building of a plant here, for example. What's very typical nowadays, for €1 per 1 peak, you can build a power plant with that. And this is the irradiance. If you have, for example, here Rio de Janeiro, 1,800 kilowatt hours per square meter per year, you end up at costs in the vicinity of €6-7 per kilowatt hour. And this is the diesel price, so well below the diesel price. So you are really much cheaper than diesel production. If you buy your model more expensive, then you have to consider the price. So this is a chart which shows you that surely this is the diesel price always changes. So this is from 2012. Now it's a bit cheaper, but it's increasing again. So therefore you always to update such graphs. But with just a graph you can calculate the profitability of PV power plants versus diesel. This is also the thing what we said. Next part is also you can use the PV as a building material. So you don't have to think about power plants as you do normally. You have to make a fence, you have to buy land and so on. If you can immediately implement it in the city infrastructure. So you save costs for transmissions because the point of generation is a point of consumption. And also you can save costs for building materials. Let's take a look, for example, this is a facade in Berlin. So you just see half of it is now photovoltaics. They didn't put here because there will be shadowing here, so they put this half which is really good insulated. Or here, this is in Eastern Germany, so just all covered with photovoltaics. It even serves as a shadowing element, so you save some costs for the air conditioning. Here you see that, so here is some shadowing here. So this is the double use. You don't pay only for photovoltaics, you substitute some other building materials which you should use instead. Here's also a roof here by photovoltaics. They even considered a semi-transparent roof. So where it's much needed, they have glass. Where little light is needed, they put the distance between the solar cell a bit higher. Where they don't need any illumination, they put the distance between the solar cells a bit smaller. And so they use that for directing the light, for regulating the light, controlling the light. We got was during that time in 2002, it even was the largest solar roof in the world, 10,000 square meters covered. But also that nowadays, so this company Asola, they invent more new. They go bankrupt recently, though they're bought by Chinese now. I don't know how long they survive. It's been a problem. They're good, but too expensive in a way. So these are some impressions of them, how was their idea integrating into architecture. But the architects have to know, so therefore we're teaching here with because sometimes they don't know, they think it's expensive, but it's not expensive anymore. It's the same cost as normal building material. This is a software PV tool. It's a video, so I don't want to show you, otherwise it needs a lot of time. So I can download it on YouTube and so on. So it shows how you can use Google Maps and use the 3D option of Google Maps in order to get this data into the PV Sol and then calculate the. Shall we? Who wants to watch it? No. We skip that and then we have more time to. For the rest of the lecture. Performance optimization. So yield prediction we already talked about, how we can predict the yield. Not going anymore, what's happening? Okay. So this is about the energy flow here. We just take a look at how we can optimize the photovoltaic output here. One part is to increase the optical part, to reduce reflection and so on, or to optimize the thermal part. So we said it's too much electrical, so we did something for the mechanical engineers. So this is about the heat distribution inside the solar module. So here is the heat flux here going to the surface and being distributed via convection and via heat radiation. So this is the radiation part, and this is the convective part. The formulas are really quite complicated. I don't want to discuss in details with you, but you can make a nice model, this was part of my PhD thesis there, to make a model of it, to really get an accurate estimation of the actual temperature, operating temperature, which determines the efficiency and then the electrical power output of the system. just go quickly over that, just as a different project. I don't want to explain in detail. So, but this works really well. We tested that model here. So this was the calculated part, and this was the measured part. So you see the deviation is here less than 1 degree. Here it was a bit big here because the wind, there was a wind coming up because it was constantly calculated with 2 meters per second here at 2 p.m. There was a high wind gust, and this led to reduction of actual cell temperatures. Vice versa, it has been at 4 p.m. There was a stop of wind, and then the temperature went up. So, but in general, the models works quite well. It's quite good for yield prediction and so on. So this is a model that we made by that. So this is a model inclination. This is the time of day, and you see the performance, energy, the PV conversion efficiency during the day. So you see here, morning works quite well because temperature are low, and then efficiency is dropping significantly because it's a horizontal model, and the heat cannot escape from the backside, and so efficiency is really low in the afternoon. If you incline the model a bit, for example, by 30 degrees, you see that immediately the heat can escape from the backside because there is a heat flow, and therefore efficiency goes up. But this you can optimize not only by terms of irradiance, you can also optimize it by terms of thermal optimization of PV system. Interestingly, here before sunset, there is some diffuse irradiance. This works quite well because the model is cold, and here you have got a very small optical efficiency because you have high reflection. Because in the morning, the sun is quite low, the inclination angle is low, and there's a lot of reflections there, and therefore here there is an efficiency drop here in the morning. As soon as the sun goes up, the efficiency also goes up. This was the model where so here you can optimize, for example, this was a work I did also in my PhD thesis to work with the combined refractive indexes. So you have the refractive cover, the first cover, which is usually glass, with usually 1.54 of refractive index, and here the next layer is the EVA, the plastic before the solar cell, which has a refractive index of 1.54. So this has a total transmittivity of about 0.86 and 0.87 percent of transmittivity. You lose about 13% maximum. I know maximum would be here at 0.89, so you can get 3% more of power output if you would optimize the refractive indices by using a low refractive glass in a high refractive plastic here. It's more extreme if you go for an incidence angle of 80 degrees. So if you have a model and there's a flat incidence angle, you have a higher reflection, so you're losing about 44% for real PV model here. If you would really have a low refractive index and the first part here, 1.1, so you would gain a lot, about 25% more power if you would have such materials which would be able to reduce that reflection by this especially low refractive index here. Yes, we made such models, just with a cool model. Some people asking me about hybrid models. Yes, we did already. So this is an acrylic tank here. We attached to that. We call it thermal enhanced PV module with integrated standing because we want to save costs by integrating the foundation here. So altogether this weighs about 150 kilos. So you don't need any additional support for that model. You just put it there, fill it with water, and it works. And this is the results. So this is a conventional model with multicrystalline cells. This is one with monocrystalline cells. So this temperature is quite high. This is the ambient temperature here, and you see here the water temperature in all-in-one solar home system is in the vicinity of the ambient temperature. So we have a significant reduction of the operating temperature. And this helps a lot for increased energy production. So we get about 8 to 10% more energy output by that system. So if you consider here the temperature coefficient here, remember here, then you get more efficiency. We did an additional thing. This is made in Rio de Janeiro, the roof of the copy here. We put water filter on the back side, we put on the front side here. So, so first effect is, sure, it's getting cooler, same effect on the back side, but additionally, water has a relatively low refractive index, so reduce reflection by this additionally. So we have two effects, optical and a thermal effect. You see it already here, the reflection here, this appears to be brighter, and this is darker. That means here more reflection here. Sorry, less reflections here. And this is the result. So you have here the efficiency. So this is a dry module here. We have efficiency of 11.5% average. This is here 12.5%. So 10% more of conversion efficiency by that measure. So this can be implemented in large scale. We didn't do it yet. So if someone has an idea to do it in a large scale, this would be really. And it looks also nice. If you can absorb it, it's a more kind of meditation actually, more waterfall. That's not consuming a lot. I think we just have a small aquarium pump, which is just 1 liter million or whatever. And I told you here, this is the cost here, that the yield installation support structure, how we can reduce that. To mention here, batteries also cost. So this we made also in Coppe, in Rio de Janeiro, so we integrated the model with the water tank, but also the battery and so on, in order to avoid the installation costs. So it could be prefabricated, and then you have all-in-one system which you just put on the roof, and there's everything integrated. You don't have to install anything. And also, if the battery is kept cool, the lifetime of the battery is much longer. So here the results. So the cooling effect is also quite good, not as good as the other system, but it was also quite good. So this is the global irradiance and the temperature, and this is significantly lower than a conventional solar home system. So this is on the Copacabana here. You see there's a pyramidator, this is the two modules and the cooling here. And you get about 9% more energy yield. You have increased reliability because it's pre-installed. You cannot do any problem, any faults by installation. Fixation obsolete. You don't have to make holes in the roof, which may allow the rain to penetrate in the roof, and also very quick installation. Can save costs in that direction. The BOS system costs. So now we're coming to another chapter. So we talked about efficiency improvement. On one side, to create more power within a certain time. But the other idea, how we, even if we have we used all efficiency measures, but how we can extend the time where the model is performing. So usually we have 20 years, but why not think about 30 years? So the cost of energy will be also reduced by a third if you would extend it to from 20 to 30 years. And this is an issue of durability and quality of the PV modules. So we talk about some typical problems, what occurs, what tests are available there, and countermeasures. So we have the standard IEC test. So this is performance under stress. So we have the IEC 61 to 15, same norm about, but only for thin film. Then for safety, we have the IEC 61 730 and the UL 1703. And we have non-IEC tests. These are special purpose tests. For example, for extreme sites at seashore with salt, or desert with sand, or farms with ammonia. If you have porks and so on, they emit a lot of ammonia, and they can be harmful to the backsheet material of the solar modules or the cables and so on. Also untypical loads, some regions they have extremely high amount of snow or hail, so this could be also tested apart from IEC. Then we have newer tests, combined loads, multi-purpose tests and so on. First we want to focus on the standard IEC tests. There is a certification in Brazil which takes one part of that only. So it's 3 tests of that. It's not the whole IEC certification, but a part of that. So it's not taking about durability, it's only considering performance. This is the whole tree of the IEC tests, performance and lifespan. So we split that up. So we first take a look at that one and then at the second one, otherwise I think you can't read that. And The yellow one are for safety. This is IEC 61730. So less important. So some of the tests are really made by the Americans. Some ridiculous tests for every purpose that they cannot cure. That if you cut the water by a knife, then you cannot take electrical shock and so on. So I won't go in details for that. I'm more concentrating on the blue side, which is performance and lifespan. So this is the first part, the upper part. So usually for testing the model according to IEC 215, you get models randomly do some preconditioning with 5 kilowatt hours of irradiance per square meter. That means in summer you sufficient 1 day to keep in Germany in the sun. In winter it's not enough. Germany we don't get the irradiance, so we ship them to Cyprus to get some solar irradiance and we ship it back to do the preconditioning. Then we perform a visual inspection, so it's kind of a report where we say whether there are bubbles, whether uninsulated parts and so on, and see the optical quality of the model here. And then we do the STC power determination. STC, remember, this is standard test conditions. That means we apply an irradiance value of 1000 watt per square meter on the module perpendicular. We make sure that operation temperature of the module is at 25 degrees Celsius and the spectrum is equivalent to AM 1.5. And then we measure the power output in the maximum power point. And this we can perform, and then we check it against the actual labeling, for example. Sometimes the labeling is not correct, and if you do your measurement correctly, we have a testing laboratory in Berlin, so if you're interested here, Photovoltaic Institute in Berlin, so we are certified testing lab, so I do this beside being professor here in Paderborn, but at the moment I stopped this activity, but still this company exists, so called Photovoltaic Institute, does certification on heating models. So this is an insulation test, so you perform at high voltage, and you have here high voltage test to check whether the insulation works correctly, there is no leakage current, and wet leakage current, you do the same underwater to see whether if humidity enters, whether the insulation is still given. And these three parts is part of the part of only, that's the entire metro certification. You get, if you want to import modules into Brazil, these have to pass this part here, these three tests. The other parts you don't have to consider for Brazil, but I would strongly recommend it to do this because this gives a lot of information about quality. Usually, most of the modules in the world market already have this certification. So you have here, for example, UV preconditioning test. So you have a UV ultraviolet source, and you see whether the plastic is getting brittle if you put a lot of UV radiation to it. You see some 10.1. That means you repeat the test visual inspection, you repeat power determination, and so on in the leakage test. So you see whether the modules after these tests is performing worse than it did before. Same as a thermal cycling tests. That means thermal cycling between minus 40 degrees and plus 80 degrees. And repeat it for 50 times. And then you see whether the module suffered by that, by repeating thermal inspection and the visual inspection and measuring the power output. Also, you have the damp heat test. For example, here it goes to 1,000 hours, kind of sauna at 85 degrees Celsius, but at a very high humidity, at 85% of humidity. And 1,000 hours is 1.5 months. Many modules fail there, and you can check that by doing visual inspection and power output. Very often the leakage current is too high. Then you have here the hail impact test. Then you see the hail cones, which have an hail impact there. A mechanical load test. You see whether you put some mechanical load on it. whether the model suffers by that. These are some kind of outdoor tests where you just using the data to measure the temperature coefficient. You have outdoor exposure test of 60 kilowatt hours. NOCT, remember what that means? Nominal operating cell temperature. So you see the more realistic NOCT temperature here and performance here at NOCT. Then you have one module where you don't perform any test at all. It's kind of control module. You keep it as it is for later purposes. This is the other test. So this is conduit bending test, partial discharge, and turbulent knockout test. As I told you, this is not so much relevant here. There's a module breakage test. That means the modules can break, but the splinters of the glass, they are not allowed to be bigger than 6.5 square centimeters. So nobody can hurt the module breaks and so on. Fire tests. The module has to be a quite expensive test, costs $4,000, but the end is always the same. The module doesn't burn, but you have to perform it according to the American norms, which is here the IC 61730. So you have to do this test, you spend $4,000. You know the outcome already in the beginning. It doesn't burn, but you have to perform this fire test in order to succeed. Come to the second part here. This is the other parts of EFP thermal cycling, and then robustness determinations. Here you see the bypass diet tests. So you see whether the bypass diet is strong enough really to survive even a load which is 25% higher than normal load. A hotspot endurance test. So you see whether if you shadow one cell, whether it's causing such a high temperature that the cell will burn. Then again, we have leakage test, mechanical load test. This is equivalent to about 250 kilograms per square meter, or for a conventional module with 2 square meters, it's about 500 kilograms and so on. So these are the tests the model has to perform in order to achieve the IEC 61-15 test. Another here, thermocycling tests, 200 times and so on. And after, if you get a model which achieves the test, it's not really bad. So it really is. It's not one of the really bad models. You have the same for the thin film modules here. It's very similar, but while the thin film modules is always changing in performance, if you have different temperature and it. Sometimes this is reversible, sometimes it's not reversible, so it's a bit hard to perform really power test. So they leave out the power test and do it just at the end. This is a procedure called light soaking. So you keep the model for 24 hours in a box with a lot of light, no, 48 hours with a box of light, then measure the power output, then put it back to the box of light and see whether it changes in performance due to the light treatment. And this you do only at the end because it can take a week or so to do the test. And then it receives that seal, the IC 61646. These are some failures, what occur frequently. So for the thin films, most of the failures have been due to the mechanical load test because they are very large scale and sometimes they break here. For the also light soaking makes a problem, damp heat makes problems. Here for the crystalline modules is the most critical test, is the damp heat test and the thermal cycle test 200 times. So quality risk along the value chain. So we have the value chain here. This consists of raw material production, module production, transportation, installation, operation. What can occur during that part? Let's take a look. So you have imhomogeneity and impurity of the raw material, it's sewing, if you saw the wafers and so on, handling on transport to the module factory, so they can already, wafers can already have some micro cracks. Module production can also be handling of cells and micro cracks, soldering, lamination, which is quite critical because it depends on temperature, it depends on pressure, and it depends on duration of lamination. Inappropriate pattering, incorrect declaration, whether voluntarily or purpose, stapling, vibration, hints during transport, this can also cause problems. Also installation, unpack, unload, unpacking, treatment during installation, fault in electrical installation or mounting can be made incorrectly. And also during operation, so there could be mechanical stress, thermal stress, or stress by ultraviolet radiation. Straight tracks, we've been discussing with Indian here. This can occur also due to this here to the microcracks which already occur there, or microcracks which occurred during rough installation. PID, potentially induced degradation, is a relatively new effect which has only been discovered some years ago. I will just go into details a little bit about that. So let's start first with the microcracks. So what is microcracks? How can you identify them? Lamination, and then we discuss hotspot and PID. So microcracks. How you can make microcracks is so small you can't see it. That was called microcracks. How you can make them visible? There's one method, it's called electroluminescence. That means we do not operate the solar module in a photovoltaic mode, we do the opposite. We feed electricity into the solar module and it starts to work as LED. So it starts to glow here, and we cannot see it because it's infrared. So we take an infrared camera and take a picture. Everywhere where it's light here, it's also working quite good in the photovoltaic mode. So here you see there's a crack here. This is isolated. So this is a crack here and a crack here. So this part of the solar cell is dead. But it's quite module, so it's not so bad. So if you stand on the module, you see damages like this. So here, these areas are dead. So these are invisible cracks. So they're very small cracks. You cannot see it visibly. But due to this electroluminescence method, you can make them visible. This we started in the Photovoltaic Institute in about 2005 or 6, 6 or 7. Now it's basically all major manufacturers adopted that method, and they always take electroluminescence method. It has been known for a longer time, but it hasn't been so much applied for photovoltaic quality control. It's a very helpful tool and very simple tool. Works very fast. You just take you can even modify a conventional camera and put away the infrared filter, and then you can have here pictures like that. So this is a video by NRL, but we skip that because we don't have such a lot of time. So this is from Photovoltaic Institute here. So we have here a module with perfect and non-critical things. So here you see how it looks like. This is due to impurities in the multicrystalline material, but this is not critical. Here you see the critical part. Here this part is dead, and here is really serious damage. So we use a lot of power, especially a lot of current. Remember, when there's current reduction, it blocks also the other cells. So if you have one damaged cell, this is getting really serious also for the other cells. What relevance is that? So first of all, if the manufacturer has problems with the microcracks, this usually before the modules leave the factory, you measure the STC performance of your module. Then this performance, this power output is put on the label. If the microcracks, the factory output is reduced. So instead of having a 300 megawatt power production facility, you have perhaps only a 250 because so many microcracks occurred. For you as a consumer, it doesn't matter so much because you get less power and you pay also less for the modules. Instead of having a 300 watt module, you have maybe only a 240, 60 watt module, and you have at a lower price. So this is relevant for the manufacturer, the direct financial loss, not so relevant for the buyers because you purchase power at STC. But there could be some further reduction in power possible, where the increase of these microcracks, they can propagate and then cause nail tracks and other problems if you do not pay attention to that. Therefore, it's quite good to do this electroluminescence analysis. Also during transport, so STC performance getting lower as a nameplate power. This is also relevant for buyers because you paid money for your STC power and now you have reduced power output. So it's a direct financial loss for you. Entering installation about the same. So it's relevant for buyers and installers, so it's directly financial loss. And operating in the field, so the energy yield is lower than expected. And there can be also direct and indirect losses. For example, you have an increased hotspot risk due to this the microcracks. Also, you mentioned this slave tracks on the Europe. Here you see first we start with the production here. Here you see what can happen if you have usually if you can identify them by seeing this is repeating things. So this is usually at production. This is a typical pattern which occurs during production in microcracks. This is during transportation. Usually, if the middle is vibrating because you transport it horizontally, you have here some cracks. Here, this is a more stable construction. Can influence that if you use more thicker solar cells. Here, you have, for example, a small, thinner solar cell, and this is more sensible to cracks, while the thick solar cell here is less sensible to cracks. Here you can also design a little bit. Here see make thicker glass and thicker frames and so on. So this you can also reduce the stress factor. Lamination can cause stress. Also lamination is also a problem with the durability of the module if the module is not clean. So you know, the every gluing process, if the surface is not clean, it won't last long. This you have to make sure in order to get a good module. Also, the plastic material, the EVA, has only a limited lifetime before processing because the additives will evaporate. So you have to make sure that you use it in a usable lifetime. The storage condition is important. There could be some oxidation of the material, also some evaporation of the solving agent, and also the quality of the supplier. Some supplier have very bouncing quality, so this makes things also difficult to have a good quality. Lamination process, the curing. So this depends on temperature. Some of the manufacturers, they save time and money because they lower the temperature because they think it still will work. And then the curing will not occur. Also temperature distribution. Some of them, the manufacturer, they use very cheap laminators, and then the surface is not even, or it goes during the lamination process, and then some part of the model is hotter, some part is less hot. No, it is the same as cooking. If you have a cheap cooking plant and then some part of the pan is hotter, some is colder. If you have a really good cooking plant which is really heavy, then the temperature distribution is more equal. Same issue here. Duration, so in order to save cost and time, sometimes manufacturers, they don't do the duration which is necessary to carry out the correct curing process. Pressure also makes problem, also the homogeneity I've been mentioning already. Quality checks for lamination, you can do the step heat treatment, but the problem is it takes 1,000 hours. So it takes 1.5 months until you get the results at least. So this is not much. So what you can do a chemical analysis to check the state of polymerization of the EVA. But the problem is that even if the lamination is carried out, we can check this, say it's totally polymerized, but if the surface is not correct or the EVA has been polymerized before the actual lamination process, your module will not be able to withstand for a long time. So this is also a big problem. So therefore, we had the PI, we could use a peel test. So we measure the force to peel off a layer of the laminate. And What's happening? Jump back. So we peel off the layer and we do a gel content test. There's also, if you do the gel content test of the state of polymerization, it depends on the number of cycles. So we compared some laboratories, some of them, they, in order to save time, they do not wait until the result stabilizes. They do it before, and sometimes you see that it appears to be 50% polymerized, but in the end, you find out only by 20% polymerized if you wait for the end results of the results. The correct result only occurs after 200 cycles. So if you choose a testing laboratories, make sure that they do 200 cycles to really get the correct results. This I was mentioning, this was the peel test here. You cut the model here and you peel off the model and you measure the force here, Newton per centimeter, and this is an indicator how good the lamination is being made. Now come, we have still time, but we are almost at the end. Just a finished PhD and then we open for question. PID, potential induced degradation. You see here the electroresistance picture, so you have here both models. These look quite nice and these don't look nice. This is a quite interesting effect because this depends on the electrical potential versus ground. This is due to the increase of system volts and the using increase of transformer-less inverters. So there's now this wasn't really so much relevant before because nobody cared about it, but now there's a really tight yield optimization. So what happens? So you have here a negative and a positive pole, and what happens there is depending on the leakage current, there is a movement of sodium ions from the glass or from the anti-reflection layer into the electrical field region of the solar cell. This weakens the electrical field in the solar cell and therefore introduces power production of the solar cell. So this happens, you have to have a high voltage. Before, 20 years ago, nobody was discovering it because the voltage had been much lower. Also at climatic, depending on the climatic conditions. And usually these are special Brazil conditions. You have here high humidity and high temperature, which lead to a high leakage current in the field, and which lead to a high PID effect. Also some modules are susceptible to PID, so this depends on the solar cell, the model design, others are not. The accumulation of sodium ions from the glass to the cell and interaction at the PN interface. So this is as parameters there's the system configuration, the weather and climate, and the specific PID susceptibility of the modules. Here you see, for example, at zero humidity, like in Sao Paulo now, that happens nothing. If you have a lot of humidity, like often in Rio or something like this, then you have a very strong effect of this PID effect. Then there's a high leakage current, and then a lot of sodium ions block the PN interface in the modules. Also temperature effect here at 25 degrees happens almost nothing, 3 degrees power degradation. If you go to 85 degrees, 95% of the power. This is a very extreme case, so not often, but it occurs that you have a high power reduction. And so this is the detail here. This is the movement of the ions. So it's a nice work to make PhD thesis on the physics part. How this is really occurred is not completely understood, but mostly understood. So if you block this leakage current, you don't have this problem anymore. So therefore we need some research at PI to find out test conditions at 60 degrees and 85 degrees. So we invented a test here, so together with other institutes. Also this depends on the anti-reflective layer, the silicon nitride layer. So this is a function of the refractive index, so it depends on the nitride and the sodium here, sodium content of the anti-reflective layer. You see there are a lot of PID. If you have a low refractive index, you go to high refractive index, there is no PID effect anymore. So avoiding the accumulation of sodium ions above the NP interface. So you can block it via polyphene, depending on the plastic you are using, or by conventional EVA, to increase electrical resistance. So just avoid the transport of natrium ion. And this also depends on the voltage. So here, if you have a lot of negative voltages, this occurs. You can ground that voltage. You don't have any negative voltage, but the inverter has to be capable to do that. As you come to that, so this is the voltage here, 100%. So you have minus 1000 volts. This is severe. Even occurs at positive voltage, but to much lesser extent. This is CIGS, not spherical crystalline, so the thin film model, which occurs. So we have a test procedure to do that. So we do electrical resistance analysis. We keep it at minus 1000 volts for 48 hours, and then we perform a power output measurement again. And so we classify the modules. Class A, where the power drop is less than 5%, and Class C, where the power drop is more than 30%, and Class B in the middle. You see the grounding of the negative pole also helps, so we just avoid the negative polarity here, and also if it's not possible, this depends, or if you don't have a transformer, if you're a transformer-less inverter, which becomes more fashionable at the moment, becomes much cheaper, then this is not suitable to ground it. You check it first. What you can do then is to reverse voltage, to put a different voltage in nighttime there, and then you can reverse that effect. This they can cause regeneration from a PID effect here on the module level. So this is some things we carried out research here. PID can be stopped and reversed. So on. You will see the effect in the field. So here, this is electroluminescence. This is a heat picture, just a far infrared picture. So you see here before and here after. Manufacturer suppliers recertification. So this is yes, this is also electroluminescence carried out via drone here. There's also kind of movie here. But at the end, what you should do in order to make sure, especially if you make large-scale projects, you should make factory inspection, because the certification doesn't help if the manufacturer changes the production process. So he shows you a nice certification, but if you get other modules, then this makes problems. So you should be able to make factory inspection if you have the money really to very large-scale projects, and to check the models, and you have to check the model prior to shipments. Combine different tests. I showed you some of them, and also do some tests at the arrival and installation site. Maybe there's a breakage and a power reduction at the transportation level, so on. And also at the very end, you have the commissioning of the PV system, so you check the on-site performance. So you need a power meter, radiance and cell measurements to really see whether the performance of the system is okay. That's the end. So I would come now to the energy storage, but I think we leave that out, and so otherwise we wouldn't have any room for questions and so on. Please, it was open for questions. Yes?
I have a question.
Yes.
Just some short announcement before Professor Krauter answered your questions. Tonight at 7, we're going to have a reception, welcome reception, in a building near to this, the other building walk about 2 minutes. Neighbor building. Okay, at 7 we start there, right? The other thing, there is a presence, a list of presence. Don't forget to sign that up, okay, please? Yes, it's circulating, it's going around. If you didn't sign it, please go to the front desk there, and she has a list there, you can sign it, okay? And then I will pass to Professor Krauter and all the questions.
So, I have a question. It's something about the emission of CO2 from the production process in photovoltaic cells. Do you think that is something that we have to worry about it? And do you think if it's possible that the organic solar cells be competitive in the future?
So first part of the question, this depends on the local manufacturing conditions. Now most of the models are fabricated in China. So glass comes from China, the aluminium comes from China, so you have to see the local grid in China. How much coal power plants are there, how much renewable energy power plants are there. So this can easily influence. If you, for example, go to Norway, there's 100% renewable energy, then you wouldn't have any CO2. With that, in average, it's about 70 grams per kilogram per kilowatt hour of CO2 emissions to the production. But this doesn't consider recycling, because you can recover a lot at recycling, and also it's not optimized for that, because it's just at the moment the prices are relevant, not so much the CO2 emissions. For comparison, for example, if you have a gasoline power plant, it's at 700 grams per kilowatt hour. If you have a coal power plant, it's 1,000 grams per kilowatt hour, or a lignite power plant even goes up to 1,200 grams per kilowatt hour. So it's at least 10 times less than the conversion and the conventional power plants, and not even optimized. So it's not optimized for that at the moment. It's only price optimized. The second part, organic solar cells. We made some tests at our university, our neighboring institute. Is that yes, they are some cheaper, but the photovoltaic part, the really converted part, is not really the biggest part. You have glass, you still need glass, you need framing, you need cables, you need bypass lines, and so on. And so this doesn't change a lot. Problem with organic solar cells is that the durability of them is not long. So after a couple of weeks, they don't work anymore, at least the ones we tested.
Thank you.
Please, it's important to identify, say the name and your country.
My name is Luana, I'm from Brazil. I studied electrical engineering. Yeah, you showed some values, but I think they were all from German. So, do you have an estimative of value of cost per kilowatt peak for PV system for installation?
Not only for Germany, the model prices all over the world are almost the same. So it is about what is that for production, and then you have the total split half-half for balance of system costs. So it's a vicinity of €1 per watt or $1 per watt. This is quite common. If you have large-scale systems, it's reduced I think to 0.8 or something like this. Or Brazil, it's just extraordinarily expensive because you have 80% import tax for inverters, which is completely nonsense. I don't know why. It's just something for inhibiting photovoltaics. But it's only Brazil. It's everywhere else you have much lower costs. So it's not only Germany; it's the rest of the world.
My name is Diana. I'm from Colombia and I study in the USP of San Carlos. I have two questions. One is about the recycling of the panels, photovoltaic panels. If you know some company that make the recycles, or if you can use one component of the panel after that it is damaged. And another question is about, I was thinking about that. What do you say about storage the energy and sell when the price is 3 times more than the during day when they produce energy? I was thinking that the only way is using a lithium battery, but because it improve the efficiency. But I was thinking about the price. I don't know if you can get a high price. This price, how 3 times more for the energy can be paid the lithium battery for that. And if it's possible, what is the payback time?
Maybe the first question was about recycling. Yes, no, there have been some efforts 20 years ago about recycling. We just do some literature research. Mr. Baumbach from my solar world, he did some tests and research about yes, it's possible. The recycled cells, they even were better than before. But problem is plastic. You have to heat up to a high temperature, more than 400 degrees, to release the solar cells. You can make it better if you use a thermoplast, but it costs more than the EVA what they're presently using. So the moment is not cost beneficial, but technically you can do that. But no company is doing that. Only one company, First Solar, is doing that because they have cut cadmium telluride modules, and cadmium telluride is poisonous, and so they guarantee you as they do recycling. So they register every project and they take back all the modules they installed. For the rest, they don't care really so much because there's no initiative for that, because the modules are so cheap and recycling at the moment is not cost beneficial. But in general, the materials they're using is glass, aluminium, backsheet, and EVA. That's a bit critical. Plastic, like having plastic tankers also, it's not really so beneficial. You can use thermoplastics, for example, thermoplastic fully return or silicone or whatever. Silicone to do that. Silicone by the solar cells is not dangerous at all, so this is no problem to dump it. The only problem actually is the plastic you have there. There's some companies like PV Cycle which do that. They take their own modules. You have to pay a fee, or if you're an outsider, you even get something because then you have to negotiate with them. But the moment is not such a relevant issue. Long term, yes, I would agree to that. Short term, it's actually nobody knows how long the modules live. Now the financial calculation is for 20 years. But actually, we have modules at the Daniel in Berlin which last for 36 years now and still working. So maybe they last longer than 20 years. The dumping issue is not so such an issue because there is no mechanical moving parts. There's just the diet. There's no theoretical limit of lifetime for that. Second part of the issue is the cost for the storage. That's possible, yes, it's possible. So there's nothing strange able to cope with this fluctuation. At the moment, we don't have this. We have old-fashioned coal power plants constructed in the 60s, which need 8 hours to adapt. So if you need 8 hours, you cannot really adapt, so they play on the safe side, so they keep them running, even if they positive there is nice weather today, and so you have a surplus in electricity. This makes the prices low and even causes negative prices. If you would have power plants would be more adaptive, then this would occur. This applies for both for coal power plant and nuclear power plant. Nuclear power plant, they have also been in the 60s, they've been set up. They were built for running 24 hours, 365 days a year with the same power output. They are not made for fluctuating. Even the thermal problems, because the turbines, they are high efficiency turbines, and if you modify the temperature of these turbines, they will break and the lifetime will be short. So they try now to really modify this to make it more adaptive, but it's really hard work. For Brazil, it will be much easier because you have a hydropower plant where you can switch off the flow more easy. It's even worse. There are some power plants in Germany, gas power plants, which would be able to adapt this more quickly, but while the price on the energy exchange bourse is so low, it cannot come because the gas power plant is a bit more expensive than the coal power plants. They emit less carbon dioxide, but this is not ordered at the moment, but they would be more adaptive. But at the moment, this old coal power plant from the 60s, also some of the remaining nuclear power plants, they kick out the other power plants which would be more adaptive out of the system because it's also called, how we call it, the system, merit order system. So you just do a sales of first of the renewables because it's by law, the renewables have preference. This is a thing that the renewable always can come in. Then you have the additional power sources and they come in order by price. And the lowest price is lignite power plants. They are in the vicinity of 3 cents per kilowatt hour because it's not possible to make new power plants for the price. This is already 30 years old power plants which you don't have to consider any investment costs anymore. They are dead anyway, so they use just the fuel costs for that calculation. The gas power plants would be much more adaptive, much more useful, but the price is at 5 cents per kilowatt hour. So they don't enter because all the positions are taken by this old-fashioned coal lignite still used on nuclear power plants. If the nuclear power plants go off, this would release that a bit, and then also more flexible power plants could come in. The price would go up, and that would trigger more investments. Another possibility would be also a CO2 price, because lignite power plants are really high emissions of CO2, and while the CO2 price is very low at the moment, they don't care about this. If you would care about CO2, then would enter also the gas power plants, which only have half the CO2 emission as the lignite power plants, or even biomass power plants or clean power plants. But at the moment they are still negotiating. Some people are afraid if you give a CO2 price, suddenly there will be a renaissance of the nuclear power plants because they say we are CO2 free. So this is a big discussion at the moment. Therefore, investments are a bit stalled, also both sides, on the renewable part and also on the conventional part. And this is at the moment the actual situation in Germany, but also neighboring countries, because they're all interconnected. And when there's a surplus in Germany, also neighboring countries suffer because they get electricity for free, and then for them they can also not invest in energy technology anymore because prices are close to zero.
Thank you. Second question and last question. Most of the panels are produced in China nowadays, but
yes.
Do you see other countries that in the future, in the near future, could be competing with China, or what do you think is just like the possibilities for the future?
I don't see anything that will change. But if you see some for instance, China, for example, the textile industry or something like this they moved to China 30 years ago or 50 years ago, and some local producers are there, but they cannot compete with China. They have large investments. I saw some factories there, so they are still scaling up. So the first power plants have been at the 100 megawatt level, now the 300 megawatt per year output. Now they're thinking about 1 gigawatt output per year and even 3 gigawatt output. The advantage in China, they got some governmental security, so they are not, they are saved by the government, so they cannot really go bankrupt. It's not that they get a lot of subsidies, as always people say they get a lot of subsidies, a dumping price, that's not true. They got just a long perspective for investments. So therefore, they can scale up. This in Germany, this was done by the grid feeding legislation, but this doesn't exist anymore. So this investment security in Germany doesn't exist anymore in any other countries. And so the big finance, they are a bit afraid of doing that. For them, it's too high risk to have a really large-scale production facility. It's not anymore the wages. In China, the wages increased a lot. And you still need a lot of more working power in China than in Germany because that's so efficient. So the cost for wages is not a big issue. Also, if you go to big factories, you hardly see any workers. It's all completely automatized. But in general, I would invest in it because this is now so much squeezed out from the cost point of view. If you get prices at 2 cents per kilowatt hour, it makes much more sense to see the value chain where you have the rest. You have to go to 30 cents per kilowatt hour and see where the rest is: storage, transmission, and so on. There you can. So even if you are able to reduce the price by half, go from 2 cents to 1 cent. For the end consumer, you won't feel difference because if your price goes down from 30 cents to 29 cents. So it makes much more, and for you as a manufacturer, it's really hard effort to reduce costs by 50%. It's hardly possible anymore. But for other parts of the value chain, it should be much more easier to reduce the costs. For example, taxes. Even in Germany, there's a high tax rate, 19%. Brazil is don't know, inverted 98. Don't know why. They said they want solar energy, but why they charge 80% for that? This can easily achieve a bigger market and also more investment. So if the investment depends on the probability and long-term perspective, and if you have this high importing tax, then the profitability is really low, especially in the high interest rates in Brazil. But interest rate is really a crucial issue, much more important than the technical issues of the solar cells and so on.
Thank you for the lecture. My name is Dago Ribeiro. I'm a PhD student from Brazil University. My question is a simple question about do you believe that solar panel, as you say, the cost of cell photovoltaic cell is getting cheaper? So you believe that the use of like a small equipment, like use because I already saw like a charger, cell phone charger with solar, like because it get be a really big market, like you make a lot of new equipment using like solar that you can just put outside and recharge for like one simple use, because you talk about a lot of like the large scale one, but like the other use is kind of like small equipment. Do you think it's a kind of good use for solar?
Yes, there's a lot of other companies manufacturing with different qualities, so I always, when I see something I buy it, and most of the stuff doesn't work really so good, so it's not really well engineered. But it's possible, and the costs are really low. So many of these small companies, they want to make a high profit. So I want to tell them, look at the solar cell. It costs only some cents. The cost of the solar cell, but for the design, the market introduction, and blah blah blah, this is always the major cost. But for the solar cells, no issue of that. The solar cell. So they want to sell just product for $20, and cost of the solar cell is maybe $1 of this product. So this is not really the main cost driver. So even if you put it down to 50 cents, there's still $19.50 left, so which could be reduced by that. You see the fair, the Intersolar fair, there are some companies there which have that, but I didn't find really a very good product yet, so I'm also looking for this. But you can make a startup and produce such things here.
Good night, congratulations, Professor, about your presentation. My name is Ulysses, I'm from Brazil. And could you talk about power quality problem? Do we choose PV system in like THD, total harmonic distortion potential of
Yes, yeah.
Sorry.
So it depends on the local grid conditions, what we have. So usually I think in Germany it's about 2% of THD are allowed, depending on the size of the power plant, and this is feasible. So with modern power electric, you don't have a problem to go. I even have some notes in German. I have some transparencies on that explaining how much the harmonics can be and what the regulations are. But this is not a big problem with modern power electronics. This is so there's a high frequency switching, and they are achieve a very smooth sinoid and with very little harmonic distortion, within 1% only, and so they are much better than the requirements.
Hello, my name is Coralie, I'm come from France.
Okay.
I have a question about the silicium resources. Do we have enough to supply solar energy for all the world, or do we have to find another material to build the PV panels?
But for conventional silicon solar cells, it's no problem at all. 40% of the Earth's crust consists of silicon or silicon oxide. So if you just take away the oxide and then you have silicon, there's no problem at all. For the doping, boron and phosphorus, also no problem, because the doping takes 1 billionth of the for the doping is required. So it's not necessary for silicon nitride. It's also no problem. Glass is no kind of big problem. So I don't see any problems for conventional. If you have some extraordinary solar cells, what is often used in space with germanium or some gallium arsenide, there's a problem, but for terrestrial applications they don't play a role at all because they're anyway too expensive. Storage, lithium is also the question that there's not lithium in the world. I've been to Bolivia, only one lake there, the Salar de Uyuni, has about 100 million tons of lithium. According to the government, the Americans say it's only 8 million, so I don't know. I took one bottle of water with me. I have to analyze it to find out what's really the content of the lithium. But apparently there's also not lack of lithium on it and other materials. So I don't see any. So for production of solar energy and for storage energy, I don't see any lack of materials or resources.
Okay, thank you.
Good evening. Congratulations for your lecture. My name is Sunny. I'm a PhD student from University of ABC, Federal University of ABC here in São Paulo, in the energy area. I worked a lot of time with R&D, and the sample I lent you is made with OPV, organic photovoltaic.
Oh, good.
Yes, and it's in a factory in Minas Gerais, a state of Brazil, and they are struggling to make it happen. They have some steps ahead of technology, but it's not commercially available yet for anybody to use it. Which would be some, advices that you could make for them, for the factory, to make it happen, keep it going, this manufacture of OPV in Brazil?
First issue is, first thank you for the congratulations and also thanks for a nice sample here, which looks really nice. But first is, if you want to attract investors, you have to eliminate the risks. That means you have to show them the product is really durable. That means you have to do a certification, IEC 61215, or in this case, Synfilm IEC 61646. Once you get this certification, you can show it to potential investors, which say, okay, this is durable and we can go for large-scale production, for example, and then produce it. Without the certification, it's very doubtful because there's a lot of bad manufacturer in the world, and the people don't trust. And this is so. At least you have to have a certain quality level and show that's a really good product, and people can use it for a long time.
They have already the certifications. They have some installations that they.
What kind of the Metro certification or the IC 61 to 15?
I'm not sure. I just know the people that manufacture. But they have some certifications. They have some installations in São Paulo and Minas Gerais, and they have some trees with leaves made with this OPV. So it's specific for curve areas. It's different. Not so efficient. But they are already selling their product. But they are still struggling to make it commercial.
I said if you want to make a commercial, you have an investor who wants to have a return of investment, and he wants to make sure that it's lasting for some time. So he has put some money on the table to get the product, and then it's generating energy, and you want to know how long this lasts. And it would be really quite interesting when it's really certified by IC 62, 646, because I don't know any flexible model which survived those tests here, what I've been mentioning. This is thermocycles and the mechanical load test. So this would be really unique, but I doubt it really, because it's really, for example, the hail test and so on. This is quite harsh. But usually, if you go to the World Bank or something like investors, they require that, even they go beyond that. They say, well, they want double IC, 61 to 15 and so on. And we work together with the Photovoltaic Institute, with banks and so on, and we discuss with them, insurance companies. And if you want to really make it commercial, they make quite harsh requirements because they don't want to lose money, and then they make quite harsh. But best is if you want to start, just to make some sample projects which you can show to them. So you say this project is really working well, show a good track record, so that it's really well, and then half of the way is already done. And then they are eager to invest. If you have it only on paper, then it's not a lot of worth. So it's just. But if you're a good sample and you can show it works for 10 years and so on, this is really quite good. If it's okay, if it's a nice, you said aesthetically appealing product for architects and so on, should go to the stakeholders there, architects and so on, and ask them to implement it. So they have some ideas where is it implemented. And, usually they are also a bit afraid of risks because they want to blame themselves, and when it's so you have to take some warranties. Say, okay, if you buy this product, we guarantee you that it will last for 10 years and so on, or 20 years. Usually in architectural projects are for 30 years sometimes and so on. So this you have to have some money to give the warranties in that direction. Okay.
Erika from National Institute for Space Research. I'm a PhD student there. What would you emphasize as a benefit and disadvantage when comparing decentralized generation and large-scale PV plants, not only in technical terms, such as proper maintenance, but also cultural, social, and economical aspects? Which one would you recommend for what local conditions?
So this is a very interesting issue. It's heavily discussed in Germany. So this is originally it was like in Brazil. It was a centralized system, but as I told you, it was very inflexible, and now people tend to make it more flexible by decentralization. So there are a lot of smaller towns which have their own energy production, quite flexible energy, and you go away from the grid. It's a bit similar to a movement what we have in the computing. So in the 60s, you had also these big mainframes, big computers, big IBM machines, and then the rest of the world was just a terminal for these big computers. And then started with the PCs, so the whole structure got more decentralized. Even the internet is decentralized. So every single computer serves as a transmitter for messages. And you don't have one single computer where all the internet is located. So this is how we call it, resilience, something like this. If you're decentralized, you are kind of more safer. So if, for example, a computer virus occurring at a centralized system, you will have a blackout all over the country. If you're a decentralized system and you can decouple yourself from the rest of the systems, it's somehow more reliable, depending on the layout of the system. But there are many other parameters. As I told, the flexibility, the backup, how you can create backup. So some regions, if you go to south, you have a lot of variation between summer and winter. For them, it will be quite hard to be totally decentralized or even autonomous, because you have to have a large storage available. For them, interconnection would be quite beneficial. Other, if you go more to the equator, where you have equalized availability of power sources like wind and solar all over the year, then it's more easy to do with less costs. But this is an interesting issue, because if you're centralized, certain disadvantages, you have the lack of flexibility, and also usually it's quite far away from the point of consumption. So Itaipu is 1,000 kilometers away from Sao Paulo, so you have to make long power lines. If you install solar panels here, you have only 100 meters here to get the power into your house, and so on. So this is both has advantages, disadvantages, yes, at the moment the tendency is more decentralized. The big companies, they don't like that, so they are putting some force against it. Why it's not permitted? And there's very old legislation from the 30s. So there was a German, what do you call it, commercialization law for energy commercialization from 1935 or something like that. Still valid. And they didn't know that it still exists, and it's still valid. So this is a lot of discussion. So because this is an old established structure, and they don't want to give it away for free, this old structure. This cannot see only from a technical point of view. But these communities, it's more what they said, which become decentralized, it's more idealistic point of view. So they want to get independent from the big companies, and they make their own electricity. So for them, it's kind of freedom. To go one step further, not only decentralized, autonomous. There's also some people which, instead of buying a new car, they're buying a huge battery, and they say, okay, I'm not connected to the grid anymore. I have all the electricity on my own at home. There's a small company in Berlin called Home Power Systems. They don't use a battery, they use hydrogen storage, which allows a storage of 1,000 kilowatt hours, which would be a really, really big battery, during winter time. So they are completely autonomous by electricity. And they have a lot of customers. It's not cheap, it's expensive, it costs 50,000 euros, because you have the long winter period in Germany. For Brazil, it will only cost 10% of that or something like this. But they have some clients, so this is also psychologically. So this is people who like to be autonomous, decentralized. If you depend on a big centralized system, other people won't like it. Did this answer your question, or you want to have other directions on this?
That's it. If you could recommend a good policy, decentralized would be your recommendation.
Oh, I think what I've been showing that the eBay for energy, this would be more fun for everyone, just to can really participate in that. At the moment, you feel kind of smooth, or you can feel you cannot really do something about this. And if you involve more people, then it could be more interesting also for the people to think about energy, and to negotiate with that, and they would have some impact. The moment, for example, they want to so-called smart grid. The big companies, they want to introduce smart grid. They take about 10 years just to define the protocol for the smart grid protocol. If you use private small companies like small startups, they will do it in a couple of days or a couple of things, and then they would be much more involvement, much more creativity and so on in that, because these old-fashioned companies, they are really very well structured, but neither flexible technical-wise, neither mentally-wise flexible. So this is,
I'm Kishore from India. I have the question on temperature cooling system for a solar. Will it help in life span of a solar if we do cooling system for a solar cell?
Yes, it increases performance, yes, but for cooling it's quite interesting. We did some research about it. Unfortunately, it didn't turn out that it really increasing lifespan. There was one, it depends on the temperature variation you have. What we found out, if we have, for example in Bolivia, if you have very cold temperature at night time, the module gets very stiff in the night. And then if it heats up, the plastic is very stiff, and then the risk of breakage of the solar end connectors and the cell is even getting increased due to the low temperature. So sometimes, for this case, if the module is hotter, then the EVA material is softer, and then the risk of breakage of interconnectors and cells is reduced. This is quite new, it's not completely published yet, but it goes into that direction. So, so cooling necessarily won't increase the lifetime. Possibly what we now working on phase change materials that reduce the amplitude of temperature changing of the module, and this possibly may, the temperature cycles are reduced in amplitude, and therefore by this would increase the lifetime. We are working on that at the moment.
And can we implement simple methods like solar farming and putting solar panels over the water canals like that?
Yes, there's some so-called agro-PV, so which agricultural PV. Put the models very high, and below that you can do agriculture. Yes, it's possible. So in Germany they made some test farms by it. It depends on the cost, how much the solar photovoltaic is cheap, but to make these towers, to fix the modules and so on, is related to some cost, but it's a good combination. So it's possible, especially for plants which require some shadows. I think coffee or cacao, they have to need some shadow, so you need some shadowing anyway, and therefore the voltaic can be quite beneficial. So that's a good idea, but no, Germany was not cost efficient, maybe in India, because they have cheaper labor and so on.
Because India having higher temperatures, more than 45 to 50.
Yeah. And it's cool. The cooling effect is also there by the plants, because the plants they evaporate water, and then the performance of the module will possibly increase also as the temperature changes. If you go to the woods, for example, then the temperature changes between day and night is also reduced. So in that case, he also would increase lifetime a little bit. You can make some tests. And you can also look at internet, go Google called agro-PV. For agricultural PV, they show some publications by Mr. Fell, Germany, who I think they made some test plans and he was promoting that.
Good evening. My name is Labi from Ghana. Please, I want to know the future of perovskite solar cells. Perovskite solar cells.
Yes.
Yeah, I want to know the future of because I know from research is saying that they have an efficiency more than 80%. So I want to know the
18%.
20%, more than 20%.
20%, okay. Yeah.
So I want to know the way forward. Is it like, is there a way that it can replace thin films and silicon solar cells in the near future?
It depends what the production at the end costs. So the efficiency is one thing, and the final production cost is the other thing. So this in Germany, my colleague Professor Resch is working on perovskite cells, so he makes also good efforts. But then the second step would be to find a company which invests in large-scale production. So one thing is having a laboratory efficiency and then putting into large-scale production. And the moment it's been missing because there are no investors in the energy technologies because the profit margin is not really high because at the moment the price is so low. So it's difficult to say. So technically it's okay, yes, it's good, but also like organic solar cells, but you have to scale up production in order to really achieve competitive pricing.
One question. The last question. Okay. A last question. Professor Krauter is very tired.
I'm sick,
Yeah, he's sick also.
No, I'm very cold.
That's ligado.
Good evening, my name is Csaba. I'm from Hungary, but I'm living for Brazil doing my PhD at UFPA. And I'm also a founder of a startup doing the Airbnb or the eBay of distributed generation in Brazil. It's called COSOL. And my question is, how you overcome the financing challenges of these mini power plants? In the case of the large power plants, we use the energy auctions where the government is guaranteeing the purchase of the energy for 20 years, so it's very easy to finance. But in our case, there is no one guaranteeing the purchase, and the price of the EV production is decreasing, so it will be the price of energy.
Yes, usually depending on the country. So in Germany, the investors are quite conservative, so they want always a track record. So the best is if you would have already a functioning scheme and have a lot of security and safety, so it's not really a good place to start up. So usually in the United States a bit better, so they are more risky and invest even if the outcome is not really sure. But nowadays, you want to go away from the conventional investors like the banks because they want a lot of securities. Perhaps why not crowdfunding? So if you have a nice portfolio where you can show also the price fluctuation and make a kit business case or business scheme out of it and publish it and ask for people to invest some money. And if you have a large amount of people, possibly it's sufficient. You don't have to wait for the bank, which usually is quite hesitant in that direction. They usually invest in old-fashioned technology. Usually not so much. But only when it gets really fashionable, like internet, when it's already the banks come also. But before that, it's a bit difficult to get some bank finance. But for crowdfinancing, so you can make a platform and you say each one is getting paying just 1,000 reais or something like this, and you get this profit rate, and so nobody's too angry when he lost his money, and but he's happy to receive quite a high return of investment. But for Brazil, in order to be it's idealistic, and now there's so many people, all you have to have a high return of investment. So as I told you, Brazil, people expect within 2 years, no, if you convince them 4 years, it's already quite good. Usually also they want to have a return of investment of at least 20% per year. Because at the bank already, if you put the money on a bank, you get 14% per year. So why should they invest for 10%, for example? This is more easy in Germany. So if you find crowd investors in Germany, the bank will get 0% or maybe 0.5%. If you're offering 5% of profit margin per year, they are absolutely happy. So in Europe or everywhere else where the interest rate is quite low. And so there are some startups which work with crowdfunding. So even in China, they make huge power plants with that you can have a kind of a pension fund. You buy single modules. So you always spend 150 euro on one module. You can buy several ones, and this will be your pension because the modules will survive for 20 or 25 years, and you always get the return of it. And altogether, they build a very huge power plant with 500 megawatts just to buy this crowdfunding.
Thank you so much. We tried that last year. There is in Brazil a government body called CVM, that's the Security Commission who is trying to protect the population from us. So I'm facing a fine.